what you're doing.
So let's switch gears a little bit. We're going to talk about exponential functions, how to do some manipulation with these. So when I say an exponential function, I'm talking about something of this form. Y is equal to b raised to x, or some other variable here. So this is opposite of something like, remember the polynomial was an x raised to a power, right? Now we're looking at the constant raised to a power of x. So this can come in a lot of different forms. So something like 2 to the x, this is an exponential function. I guess if we're thinking about graphs, y equals 2 to the x. Something like this, even y equals 3 to the x plus 1. We could still put this in the exponential category. Or even something where I can have another constant in the front. Even this we can put into the exponential category. The reason exponential functions are important is because they model growth of a lot of things that we deal with, especially things like population growth. So if you say, for example, something is growing exponentially, that's what this means. It's growing with a graph that's similar to an exponential function. So a basic exponential function always has the same shape if you graph it. So we'll graph one like this, y equals 2 to the x. We can just kind of think about some x values and kind of plug them in to see what this graph is going to look like. So for example, when x equals 0, y equals 2.
2.
Nope, not 2. Anything to the 0th power.
1.
This one? Yeah, so that's one of our rules. Yeah, so in this case, when x equals 0, y is equal to 1. And so that means I'll always have this point 0, 1. And in fact, on any basic exponential function like this, as long as there's not another constant out to the front, that'll always, well, I should say that. As long as it's in a basic form like this and we haven't done any alterations to it, then that'll always be a point on the exponential graph. Of course, here if you put in x equals 0, you'll get 3 to the first, which is 3. So this has to do with a shift in the graph. We might talk about that in just a second. So what about when x is equal to 1? Then y will equal to 2, right? Okay, so point 1, 2 right here. When x is equal to 2?
4.
Okay, y will be 4. 2 squared is 4. So right here. And already you can see this thing is climbing really fast. So like if x is 3, in this case y would be 8, which is up here in our chart. So this is why when we say something is growing exponentially, that means that at each step it's getting even larger and larger. The steps of the y values are getting bigger as the x values stay at a constant rate. Okay? So when you're, for example, if you have money that's growing exponentially, that's a good thing, right? But if you have a virus that's growing exponentially, it's a very bad thing, of course. So what about the opposite direction? What if I take like x is negative 1? And that would be 2 to the, y would be 2 to the negative 1. So what does the negative exponent mean that we have to do? Thinking back a few lectures, I think, right? This is the flip the fraction, right? Take the reciprocal. Yeah, so this is 1/2 x to 2 to the negative 1. So that means that when x is negative 1, we get this point here, negative 1/1/2. And then when x is negative 2, y would be 2 to the negative 2. So this is 1 over 2 squared. So 1/4. What will happen to all these points as I keep going?
They get closer and closer to 0.
Right, but they'll never actually
Touch
make it
ball.
to 0, right? So we'll actually say that if we graph this in this particular form, as x gets bigger and bigger and bigger, the numbers start going up uncontrollably, right? And as x gets smaller and smaller, we'll get closer and closer to 0, but we'll never actually get down to 0. Now, of course, I can do a lot with this function, right? Just like we had with other functions. So for example, if I'm looking at something like this, y equals 3x plus 1 to the x plus 1 power, how would I deal with a graph like that? Well, all of these graphs in their basic form in the y equals b to the x have the same basic shape. So if we're looking at something like this, y equals 3 to the x plus 1, we'll just start with the base graph, which in this case is y equals 3x. It will have the same general shape as y equals 2 to the x. It'll still always go through 0, 1. Okay, all of these will. But now instead of 1, 2, if you think about when x equals 1, y will equal 3, right? So we'll actually get bigger a little faster. But in general, it will have the same basic shape. So if that's the base, y equals 3 to the x, how would I graph using that y equals 3 to the x plus 1? This one you have to think back a few lectures for. In this case, we're replacing x with x plus 1. Remember what that does to the function?
Move it up.
That's if you add a constant to the end of the function, to the entire function. So whenever you replace the x's, that's when it moves it left and right, right? And so if you replace x with x plus 1, this does the opposite of what you think. It will move it to the left 1 unit. So actually, if I want to graph y equals 3 to the x plus 1, really I can think about taking this graph, instead of the point 0, 1 being right here, it's going to be shifted to the left, right? So instead of 0, 1, that will be at negative 1, 1. And then here, instead of 1, 3 as a point, it will become 0, 3. And, if you're sketching these graphs, you just got a couple of points, that's fine for purposes in this class. If you want to get 3 or something like that, you get it more defined, but you kind of know what the shape is already. So kind of these rules are coming back on us on how to do the functions. What if I gave you something like y equals negative 2 to the x plus 3. This one's a little more complicated. But the same rules apply. We don't have any new rules on how to deal with functions. So we just start with whatever our base function is going to be. So y equals 2 to the x in this case. And we know that has a point here at 0, 1 and at 1, 2. So for this one, I need to do 2 steps to it, right? And this one, the order does matter, so we have to be careful. If I make it negative and then add a 3, that should be okay, right?
Yes.
Right, because then the problem is you don't want to add the 3 first, because then if you make the whole function negative, that'll become negative 3. So you could have done the opposite way if you subtracted 3 first, but that's harder to think about. So let's make this y equals negative 2 to the x first. So if you make the entire function negative, this does what to the graph?
Flips it.
It flips over what?
The y-axis?
So if you're flipping over the y-axis, you're making all the x's and negatives, right?
Right.
But in this case, we're taking the entire function and making it negative, right?
Okay, so that would go over the x.
Yeah, by default, right? Over the x-axis. So if you want to remember it, I always remember it by, if we're taking all of these we're taking all the y values and making all the y values negative, so we're flipping it this way, over the x-axis. So this will flip over the x-axis. So again, just make sure you're moving your points. Instead of 0, 1, we'll end up with 0, negative 1. And instead of 1, 2, we'll end up with 1, negative 2, right? And we'll end up with this. But we're still not done, right? Yeah, see, I'm running out of room here. I'll go over here. Because we're trying to get to this one. So we have it to negative 2 to the x. And now so this is step 1, this is step 2. This is step 3 now. We can add 3 to that entire function. So negative 2 to the x plus 3.
Move the graph up 3.
Right, because we're adding 3 to the entire function, right? So this will move the graph up 3. So we're taking this graph, number 2, and moving it up 3. So 0, negative 1 will become 0, positive 2. And then 1, negative 2 will become 1, positive 1. And then, actually I can find the, if I want to be really accurate with this, I could find the x-intercepts. Well, maybe we'll say, we know the y-intercept. Actually, we don't have the tools quite yet to find the x-intercept, so let's not worry about that. Let's just get the sketches of the graph. So I know it'll look something like this, right? One other thing, though, is that since this is approaching 0, right, and all of these graphs are approaching 0, we call this line that it's approaching, we call it an asymptote. So it's a line that it approaches, but it never quite gets to. Technically, I should have been moving this asymptote along with my graph. Right, so here, the asymptote stayed in the same place because I just flipped it over the axis, right? But here, where is the asymptote going to be?
3.
Right, at x equals 3, right? I'm sorry, y equals 3. So there's my asymptote here, the line y equals 3. So you should technically move that asymptote along with it, but it's pretty easy to move because you only have to worry about going up or down with it. It'll never like turn slanted or anything like that in these types of problems, at least. So basically, we can take these exponential functions and just take all the rules that we did from a few lectures back whenever we were moving functions around. The same exact rules apply to them. You just have to be careful because it's a new type of graph and make sure that everything's moving along with it. Now there's a special base, or maybe I should mention this before we move on. If you take any graph of this function, y equals b to the x, we already said they all have that similar shape, right? But in fact, they all have this same property, where they'll go through, first of all, 0, 1, right? And there's one other point you can always figure out what they go through. Do you know what it is? Or they can figure out easily what it goes through.
1b.
Right, exactly. The other one was 1, 2, and 1, 3, right? So here, 1b, because b to the first power is that. So you can always figure that out. And you can always have those 2 points fairly easily to figure out the graph. So something like y equals 4 to the x. If you need to sketch that real quick, you automatically know it goes through 0, 1, but you also know it goes through 1, 4. And then you have a good sketch of the graph. And then you know it still has the asymptote, of course, here. All of these have the asymptote along axis. Now there's a special base that comes up a lot, and that's the natural number e. E is an irrational number, kind of like pi. It goes on forever, doesn't repeat, doesn't terminate, but it's approximately 2.71 if we do some rounding. And so E is a very important base because it comes up in a lot of natural phenomena, so natural growth curves and things like that. So we actually end up using it a lot as a base. So the graph, the base graph y equals e to the x becomes a pretty important graph to us, and you'll see why in a couple minutes as to why e is a pretty important number. But don't get it confused with a variable. It's just treat it like you would any other number. Treat it like you would if you were dealing with pi, for example. So what was the graph of, using what we just talked about, what would the graph of y equals e to the x look like?
Well, it would go through 0, 1,
Okay.
and 1, 2, 2.71.
Right, approximately 2.71, right? So it goes through, really, if we want to be accurate, it goes to the point 1 e, right? So about right here, maybe? And so typically whenever we use e, we don't want to use the estimate of it, except for when we're trying to figure out, for example, I know it's between 2 and 3, and so I'm going to put that there on the graph. But try to be exact with your answers. Don't try to round e and then multiply it into an answer or something like that. So this will be a graph that you'll see quite a bit, y equals e to the x, but it graphs exactly the same way. It's just 2.71 approximately to the x power. So same thing as before. So one situation in which these exponential functions come up is dealing with interest rates, things like loans or just putting your money into the bank. So if you're investing, for example, into a bank account, most banks use what's called compound interest. And to figure out how much interest you're going to make over a certain amount of time, they use this formula here. A is equal to P times 1 plus R over N to the N times T power. Okay. So what does all this mean? Well, A is the final amount that you'll have. Okay. P is your principal, so how much you invest. R is the rate, so the interest rate. N is the number of times compounded. We'll talk about this in a second. Per year. And then T is just the number of years. Okay, so time in years. So if you're doing like half a year, for example, T has to be 0.5, not 6 for 6 months. So what do I mean by compounded by a certain amount of times per year? I'll give you an example if you're not familiar with it. Let's say that you have $1,000. You're going to put that into the bank, and just to make the calculations easy, let's say that the rate is 12%. You can find a bank that has 12% interest. That's pretty. I'm having trouble finding 1% interest right now, right? So they're all pretty low. Maybe if you watch this video in 5 years, it'll be better. But right now, there's no way you'll find 12%. But just to make the calculations easy, let's try that out. So let's say that the bank doesn't compound on a regular basis, or we'll say they compound once a year. Okay. Okay. So that means at the end of the year, they're going to take 12% interest. Right, so they're going to take your $1,000, multiply it by 0.12, And so you end up with $120, right? And they'll tack that onto your principal amount, so you should end up with $1,120 at the end of year one. This is what's called simple interest. But most banks don't do that. Most banks compound monthly. Okay. So let's look at how this value would change. If you wanted to think about this, you're getting $120 at the end of the year, right? Or you're getting $10 a month. That's another way of thinking about it. But when a bank compounds monthly, it actually takes this percentage and splits it up over 12 months. Okay, so each month you're going to get a 1% interest rate. So now at the end of month one, for example, take that $1,000, you get 1% of that, so you get $10, right? Okay, so at the end of month one, you're going to have $1,010. But now, since you're compounding monthly, at the end of month two, they're going to take another 1%, but they're not going to take a 1% of $1,000. They're going to take 1% of however much you have in there after it compounds, right? So now they're taking 1% of $1,010. So now your interest that you earn is not going to be $10 for that month, but you're going to get $10.10, so slightly more, right? And so now at the end of month two, you'll have $10,020.10. And then this keeps happening. So now you take whatever interest you have here, and you're going to take that percentage of that. So now for the third month, you're going to take 1% of $1,020.10. So now they're going to take $10.20, 201, I guess you would round it to 20, right? 10.20. And so now you have $1,030.30. The idea is that now when you get to the end of the 12 months, you're going to have more than $1,120 because you're not only adding $10 a month like you were up here if you thought about breaking the months. You're adding $10 plus more and more every single time. So basically you're taking interest on the interest that you've already received, and that's the idea of compounding monthly, right? This is what most banks do. So if you want to figure out exactly how much you'll have at the end of that time period, you can just go directly into this formula and it will tell you. So if we want to look, for example, how much would I have at the end of, if I invest $1,000 at a rate of 12%, so R would be 0.12 here, compounds monthly, right? So N becomes 12, and then N again is 12 up here. And if I'm looking at the end of 1 year, then my time is 1 year. So now I can just figure out what we're going to have here, right? So at this point, we go for our calculator. Or sometimes you might get one, or you might get them to where you can just do them in your head. But so I'm taking my 12 divided by my 0.12. Of course, that's much, in my head I'm thinking that's hard, but it's only 100, right? So this becomes 100, and this plus 1, so 101, all raised to the 12th power. Oh wait, I'm missing a decimal here somewhere, aren't I? Oh, I did it backwards. Of course, this is 0.01. That'd be a good one for the tape, the blooper reel. So this is 0.01, right? Raised to the 12th. So now my value is going to be $1,000 times 1.01 to the 12th power. So 1.01 raised to the 12th power is approximately 1.1268. And if I take 1,000 times 1.1268, I'll end up getting $1,126.80. So if I compound monthly instead of compounding yearly, I'll actually end up making $6.80 more than I did, right? Which is not, not significantly more in this case, but if you're thinking about if you have $1 million in the account, then all of a sudden you're talking a significant amount of money that you can make. And like I said, most banks will compound monthly like this, and so all you have to do is plug in to the formula, and you can figure this out. Now, of course, some institutions will compound yearly. I'm sorry, not yearly, but daily. Right? So if you're going to compound something daily, that just means that your n is going to be 365. And in fact, if you took that and compounded daily, this would be a slightly larger number as well, because it's compounding more times and you're compounding that interest on top of itself. So if you know what so this is daily. Some other ones, let's see, we already said monthly.
Quarterly.
Right, so quarterly would be another common one. So in this case, n would equal to 4 times per year. Semi-annually, in this case, n would equal to 2. So mainly, you just have to know what the n's are equal to, and then you have your time, how long you're going to keep it in there. And then you know your rate. Be careful not to put the rate in as a percentage, but put it in as a decimal point. So I guess just to give an example on here, let's say that we invest $5,000 at a 5% rate for 3 years. And it's going to be compounded quarterly. So how much money will we have? So in this case, P will be equal to 5,000. Our rate is 5%, so R will be 0.05. 3 years, so our time is in years, so we'll make that 3. Careful, if I said like 6 months, again, that'd be like 0.5 years. Or if I said 3 months, that's 0.25 years. And then, what am I missing? Oh, compounded quarterly, so n will be equal to 4. And then I can just plug this directly into my formula. So A is equal to 5,000 times 1 plus 0.05 over 4, all raised to the 4 times 3. Okay, so here we'll get 1.0125, all of that raised to the 12th power. Which will be 1.1607 or 08 if we round. So this is about $5,803.77. So that should be our total amount that we'll have if we leave it in there for 3 years at the 5% interest. So what's convenient about knowing this is if you're looking at 2 banks and like one of them compounds semi-annually, one of them compounds quarterly or whatever, they have different rates, you can kind of compare like, oh, this one has a better rate but it doesn't compound as much. This one has not as good of a rate but it compounds daily, if you could find one that compounds daily. Then maybe you end up getting more money off of the lower rate. So sometimes you'll surprise yourself. Now the question is, what if I try to trick the system, right? And I said, well, I know the more that I compound, the more money I make, right? So what if I try to come up with a system that compounds every second, or that compounds every half a second, or that compounds 50 times a second? Can I make an infinite amount of money doing that? Because that's a significant question, right? Well, it turns out there's a cap. There's a cap to how much money you can make. If you take this formula, P times 1 plus R over N to the nt power, and if you take n all the way to infinity, or you think about what happens as n goes to infinity. In calculus, we call this a limit. What's the limit of this function as n goes to infinity? It turns out you actually hit a cap that you can't go over, and it turns out in that case you can represent your value as this: P times e, our number e from before, 2.75, to the RT power. So if you compound as many times as possible, you actually get to this particular formula. So this is our compounding a finite amount of times, and this is the formula we use when we say something is compounding continuously. Okay, so if you ever see that it's compounding continuously, that's exactly what it means. It's compounding as many times as possible, actually an infinite amount of times. But you hit this cap, and this is what the formula would be. So, for example, I'm going to invest in the bank, and I'm going to invest $10,000 for 3 months at a rate of 2%, and I know that it's compounded continuously. How much is going to be in the account? Well, again, in this case, P stands for our principal value, the amount that we put in. E is just the number E. Okay, so approximately 2.71. R is our rate, and then T is our time years. So for here, I would just go in. So I'm investing $10,000, so that means that my P is 10,000. 3 months. So what will the T be in this case?
Quarter.
Yeah, 1/4 or 0.25 of a year. The rate is 2%, so 0.02. And then it's compounded continuously. So we know it's using this function. So if it says it's compounded monthly or whatever, you have to use the first function. You should know in the problem it should tell you how it's going to compound, and that's how you know which equation to use. So from here it's pretty straightforward. Once you have all this, you can just plug in the values. So I did this backwards. So this should be 0.02 minus 0.25. And there's probably an E button on your calculator actually, right? So E raised to the 0.02 times 0.25. I got 1.005, so what you got?
Yes.
That times 10,000. So approximately 10.05. So $10,050.12 on that at the end of 3 months. Not bad, $50 for 3 months. In there. Now, of course, on an exam, you're not going to be able to estimate here, so just stop right there, because that's a good enough number. Or at the when you plug in this, once you get everything plugged in, you can maybe simplify this, but you can just kind of leave it like that. I just want to know that you know how to use the formula, not necessarily that you know how to plug it into the calculator. So this is an example of when our exponential functions, right? Because it's just is an exponential function, something times some number raised to a power that has some variables in it. This is actually an example of when we use things like this. So the exponential functions actually do come in. We use them all the time. If you think about taking out a loan for the bank, they use the same kind of idea to figure out how much you have to pay per month. So what's nice about this too is also when we get some more of these tools in the logarithms section, you can figure out, for example, how much should you invest to get a certain amount out at the end. I want to have $120,000 in 7 years. At this rate, how much should I put in to get that much out? Then we can solve for that. We'll have to learn. We can't do it right now. Once we get the logarithms, we'll be able to do that. Want to take a quick break?
Sure.
Is it okay? Everything all right?
Yep. Oh, don't switch
I
cameras.
wasn't sure if you'd seen the compound stuff. I wanted to explain it all in case anybody's watching the clips. Do you have a lot left in your other classes?